Hello, and thank you for joining me for my talk. I'm going to be talking about chemical self-consistency as the next hurdle for general circulation models, or global climate models, as you will. And I'm going to show a couple of examples from Rocky 3D and some other GCMs, just as a way of hinting at where we need to go. So what do I mean by chemical self-consistency? Here, I'm talking specifically about the disposition of the atmosphere, and how it must be wholly bounded by reasonable constraints for things like planetary outgassing, installation, temperature, the dynamics, and any interactions there might be between the atmosphere, ocean, and surface. Things such as dry uptake by the surface or exchange with an ocean layer through diffusion or through precipitation. And for the modern Earth, I will note that this can be a secondary concern. It's very much so that the primary climatological drivers are mostly static in a certain sense, and not necessarily linked to a lot of these photochemical sources that would drive a lot of these changes. But we still do see an impact on the observed temperature and dynamics that is driven by primarily photochemical processes. It's particularly notable in the stratosphere. For example, the presence of ozone is a primary driver for the stratospheric temperature increase that we see there. But you also see the drive of climatological changes from chemical consequences, for example, from the ozone hole, which turns out to be the dominant factor in controlling Antarctic surface wind pattern changes, which has driven regional changes in precipitation and temperature, which in turn influence ocean uptake of CO2 and sea ice formation. Now, for the modern Earth, that is, again, a secondary concern potentially, but there are clear links between photochemical processes and climatological consequences, even on Earth. An example that we have, again, from Earth is that clouds are incredibly complex. And while I can't hope to do them justice in a single slide, they are critically important for these climatological simulations. Cloud condensation nuclei are derived from multiple sources, ranging from open ocean sea spray that lofts salt into the air, volcanically derived sulfates, organic carbon aerosols from forests, and algae, lofted dust and ash, among a suite of other cloud condensation nuclei. So if your world is abiotic, there should be a drop in cloud condensation nuclei. And for example, if it's cold or dry enough, there may not be any open water to spray salt in order to supply those additional cloud condensation nuclei either. So without cloud condensation nuclei, water takes approximately a 4 to 8 times increase in supersaturation over its saturation vapor pressure in order to homogeneously nucleate and condense, or substantial supercooling. But neither of those is observed in the modern atmosphere. We have a surplus of aerosols on which water does condense. Some cloud condensation nuclei are more effective than others. For example, sulfate in organics are much more hygroscopic and take up they take up water more effectively than other aerosols like soot. But the whole suite of CCN does work as condensation nuclei by definition. Lastly, it's important to note that there is a substantial human contribution to modern CCNs. And then so from the from the panel on the right that I'm showing you here, from the modern sort of atmospheric monitoring that we're seeing, you see some biological sources for aerosols, for example, organic aerosols or ammonium aerosols that do have some human influences. But you also do see some that are predominantly rural or anthropogenic, like nitrates. And then you have some pools that are a combination of factors that are driving them. So sulfates are volcanically derived, but also derived from biological and anthropogenic sources. So for an abiotic planet, just to return to that, there is the potential that you could decrease the amount of cloud condensation nuclei just by changing whether or not your planet has life. And I would point you to the literature for Colin Goldblatt's work or Benjamin Charnay's simulations of what that might look like. I'm certainly not going to wade into what's been approximately a decade-long discussion in the literature regarding that. Now, following on from that, we do see that there are other drivers that affect both climate and aerosols. So take, for example, the left panels here are for a regularly 24-hour day Earth that has a zero eccentricity and zero obliquity, and the rightmost panels are for an Earth with zero eccentricity and zero obliquity that has a synchronous rotation, as in one side of the planet is permanently fixed to the sun. And you can see that distinctive eyeball pattern that we've seen in a lot of other places. But what you can also see is that we fundamentally changed where we're sourcing particular chemical constituents, like minerals, which is in the middle row here, mineral dust to the atmosphere, predominantly Saharan in the modern, but now shifting to this synchronous rotating state, you can see that Australia is the predominant source of mineral dust to the atmosphere. And likewise, the proximity of open water to the substellar point is going to be the only source of sea salt aerosols to the atmosphere. And you can see that going from those latitudinal bands of sea salt spray in the modern, or approximately modern case, to that substellar eyeball pattern. Now, following on from that, we can also see that where there are clouds, then there is ice along the terminator. And so those clouds and that ice paint you a very distinctive eyeball pattern, not just in terms of the clouds, but also in terms of the surface albedo, because of the distinct disconnect between the dark of the ocean and the light of the sea ice and snow. The consequences of the chemical nature of the atmosphere, because we're still talking about the modern Earth, you still have aerosols like black carbon that's being produced by biology that still has some tenuous grasp on the surface of this planet. And you can see that the differences between, for example, the one-day rotation period in the bottom row and the synchronous rotator in the top row is that there is a much more distinctive drive in the change in the ice albedo because of the prevalence of black carbon depositing on these now static persistent ice sheets. And so that's one potential climatological consequence for these even near modern scenarios. Now, if we look further afield, we can think about the climatological consequences of different atmospheric gases. And this is just a chart showing you that based on the redox or the oxidation state of the magma that's sourcing some of these volcanic species to the atmosphere, you can change the speciation. And so for the Earth, we predominantly have CO2 and water that's coming out of volcanic vents and lava flows. But as you get to more oxidized body, or more reducing bodies, I'm sorry, like Mars, for example, or even all the way down to the moon, you start seeing that you get this rapid shift away from water and CO2 to things like hydrogen and carbon monoxide. And it's worth pointing out, just as an aside, that the bulk silicate Earth and exoplanets do plot fairly reduced on this scale, just because of the inclusion of the iron core. Has a lot of reducing power. And because Mercury is mostly an iron core, it plots off the axis to the left. Now, when we think about this in terms of atmospheric chemistry and climatological consequences, we can see that for these edge cases, for very reduced mantles like the moons, they have immediate climatological consequences. So this is a paper from Igor Alenov from last year that shows that if, for example, the atmosphere is driven to a point where it is CO dominated, because there's a lack of water vapor that's going to catalytically drive the conversion to CO2, we can see that those types of planets are going to have a very different climatological state, a very strange one, albeit, than the ones that are dominated by more conventional greenhouse gases like water or CO2. Further afield, of course, we can see that for other planets, those feedbacks can be even more pronounced. M-dwarfs have a long history of hosting a slew of issues, but a repeated one is whether or not CO2 is photochemically stable in their atmospheres. And you can see here from Renyu Hu from this year, a simulation showing that if you get into these weird edge cases where you enter CO runaway, you can accumulate tens of bars of CO and oxygen in a planet's atmosphere, and it has real climatological consequences. So whereas with 1 bar of nitrogen as a background gas would be relatively stable and have a smooth transition with increasing CO2 abundance, as you increase the background gas, you get to higher and higher surface temperatures. And if you have too much CO2 and too much CO because of this photochemical state, you can enter a perfectly uninhabitable condition. And I want to conclude just with a final thought that planets are hard, and that these interconnected facets have to be in the forefront of our minds as we go forward. Yes, the cases I showed are edge cases, but where are the edges? We currently don't know the full scope of the landscape at this point, and that bounding space for common problems like the CO2-rich atmospheres for terrestrial planets around M dwarfs could produce conflicting results until we have a good answer. The Earth is an integrated system, and blindly using modern Earth parameterizations can lead to unphysical or even implausible results. Conversely, setting aside fundamental physical drivers or Earth-based tunings can also upset formerly self-consistent systems in the absence of some other driver that's going to bring that back towards balance. So I encourage all of you who are predominantly climatologists to take a couple of moments and just think about where all the connections are and if the planet that you're modeling is fully self-consistent. Thank you.